Welcome here to Gorilla Electronics. Today I will be demonstrating to you a quick and simple dirty repair of a Eurotherm Chessel recorder. This particular Eurotherm recorder has been in service for over 10 years. It has worked 10 years, 365 days, 24 hours, and it's approximately 88,000 hours of continuous service. So quite an impressive piece of engineering here. Now this particular unit was presented to me dead, as you can see currently. I currently have it plugged in, as you can see inside. I am getting an indicator light on the board. I don't know if you can actually see it. Tell me that there is power on the board. So we grab our trusty flute meter. That's our trusty flute meter. We have our trusty flute meter and we have it on DC because we already know that we have AC. Of course, we would like to check out what the DC is. So when we check out what the DC is, now I have to caution everyone here, if you don't know what you're doing, please do not do it. There are lethal voltages here, and you could quite possibly kill yourself, or at least hurt yourself pretty badly. So I come over here to the power supply. This is the power supply board right over here. It's coming off of the 110 volt main. However, this is a switching power supply which has auto sensing, which will accept 220, 240 volts, and it will convert all of our powers. So, I come over here and take a look, and I'm getting 124 volts, which here in the US, that's normal. Now, I come over here, and I switch this over here to our DC, so we can get a chance to check out DC. We check out over here, and this uses pretty much universal wiring. So, as it states here, we have black, black, red, blue, and we have yellow. So, yellow generally is 12 volts. Of course, black is ground. Red is 5 volts, and the blue here, well, we really don't know what it is, unless we know what the specs of the power supply are. I know that it's 24 volts. Now, carefully, we ground our blue, we ground our black, and we follow here, and currently 12 volts is deficient. It's 9.41 volts, and assuming that if we were to switch our meter to AC, will have some ripple in there. Okay, so we have 1.6 volts of AC ripple. So now we'll go over to our 5 volts. 5 volts is too deficient, and this is why our logic is not functioning. And we'll go here, and as you can see, we have a little bit less than half a volt of AC ripple. Now we'll go lastly over to our 24 volts. 24 volts has about 200 millivolts of ripple. However, our it's 22 volts or so. So we understand here that the power supply has the deficit. So what we're going to do here is we're going to remove the power supply, and we're going to quickly check the secondary side over here of the capacitors. And we're going to see what our filtration is for what has been converted. Give me a moment. I'm going to remove this, and I'll be back in 2 moments. So I'm back, and I pulled out the board. Here is the board here. I did remove, for time constraints, the capacitors, and I traced out the circuit. So I will explain quite quickly how a switching mode power supply functions, just the baselines of it. But we have 120 volts AC coming into here. It's rectified. As it's rectified, it's filtered, and as you can see over here, 120 volts at 60 hertz. Okay, and it looks something like this, a squiggly line, and after it's rectified, we have basically 120 hertz at 170 volts. And I have a little caution sign over here to be careful, because this particular capacitor that's right over here stays charged. Now this particular circuit they paid attention to, and they put a bleeder resistor on it, but you might actually run into a power supply that doesn't have this, so always assume that this is charged. This will give you a nasty little shock. Okay, remember it has about 170 volts on it. So anyway, when we get up to this point right over here, we have a PWM, which is a pulse width modulator, and this is actually pulsing this particular MOSFET transistor. I have I got a conventional transistor in here, but it's a MOSFET in this particular area, but it could be either or, this particular circuit. So this is actually switching this on and off like a light switch, and we're inducing a field on the winding of this particular a faux a DC field, a faux AC field on this particular winding. So over here, this is what we are left with. We are left with, if you look at this as a scope at 170 volts at about 70 kHz. Okay, this over actually goes in here. It's actually dropped down. This is actually done in such a way because they can make the transformer much smaller because it's at a higher frequency. So after this comes back here, on the secondary side over here, we have some rectification diodes. That's this big one over here on the side. You can take a look here. And then we also have the filtering capacitors. So now the issue with this particular power supply that I'm working on is the filtering capacitors. As you can see, I removed them, as I mentioned. So I took the liberty of drawing everything out. As you can see over here, I have the circuit and I removed it. And if you look over here, this C15, C14, and C16, these are all in series. And because they're all in series, excuse me, these are all in parallel. This closes the 5-volt circuit. The 24-volt circuit is the same. We have 3 capacitors in parallel, and when you add them all in parallel, that you times it by 3 or whatever the volume of yours. You add them, and then that's your C total. So 24-volt filtering is 3 times 180, which is equal to 540 microfarads. So since it's filtering, it's not that critical. You just have to have greater than 540, not too much greater. Since these are 180 microfarads, I don't have 180 microfarads lying around. Now, I don't really like mixing the value of capacitors in parallel, but in this case I'll make an exception because I don't have anything else and I need to get this recorder working so it can go out there and do its job. So what I'm going to do is I'm going to do 2 times 24 plus another 100, which will give me the 500, which will give me the 540 that I require. Now the next, which is critical here, is the 5 volts. You require 5 volts to operate the logic inside of this particular recorder. I believe the 24 volts is actually for the monitor for running the LCD. So this over here is 3 times 1500, which is 4500. Now I don't have 1500. However, I do have 2200. So I'm going to put 2 2200s plus 1 1000, and that will basically give me 4400. Now I'm missing 100, but these are plus or minus, the tolerance plus or minus 20%. Now lastly over here you have, next to last, we have the 12-volt circuit. The 12-volt circuit over here is using a filtering capacitor in the input and another filtering capacitor in the output, and this is 220 microfarads and 100 microfarads. We're going to replace that with the exact values because I have those. Now this is over here. This is not bad, however I'm going to change it because they do dry out over time and the unit has been on continually for 10 years. Now this is a starter capacitor. That's that capacitor right there. It's a very, very, very important capacitor, and it's a very important capacitor. It's part of the pulse width modulator circuit. This is another one over here. This is 100 microfarads. I would suggest changing these two just to be safe and ensure another 10 years of operation, at least with the power supply. I have the capacitors here. I did remove them. Okay, this is, as you can see, this is the 1500, and the other one here is the 180. And as you can see here, I have a scope. I have a scope too, but I have a capacitor meter and my capacitor meter, which I'm just have set for general, but this is you don't use a fruit meter or so forth, whatever you might find. I tested these, and these are basically open. I'm going to try to painfully clip onto this if I can. Okay, so this is supposed to read at 1500 it's supposed to read a 1500 microfarads. I'm reading 1.3. As you can see, there's no filtering. I'm just getting ripple. I'm going to replace these particular devices. I'm going to put them in. I'm going through some of them, and I'll be back in 2 minutes when with the unit repaired in the recording. Okay, I'm back. I managed to solder in all the capacitors. Surprisingly enough, this one was totally dead. This one over here was still good. Everything else was out of spec. I'll just tell you real quick. So I'm going to connect to my capacitors that I put in parallel. And if I could just try to find out which over here is the... Okay, so and it says open. I don't have a connection. Sorry, this is very difficult to do on the end. Okay, as you can see, that's completely wrong, but I can't do it. Trust me, I tried it before. It's fine. So I am going to take this unit now, and I'm going to put this unit in. Keep in mind that you want to remove the mains because you do not want to get a shock. The other thing you want to do is you want to make sure that you put this in properly. Okay, don't short anything out. As you can see, there's my plate. I don't know if I decided to put that in there. That's the insulating plate. In the interest of time here, I am going to just put in 2 screws. The grounding screw so that we can maintain some safety. Should invest in a tripod. Or at least a helper. Now, this recorder could have other problems if, depending upon how long the ripple was there, it could have damaged the logic on the board. I'm looking down below, and as you can see, this is going to require some work, but that's another video. That capacitor there is rounded, so that is a filtering capacitor on the board, and that is protection in case the capacitors on the board turn out to have any ripple. So that's an issue that we'll take care of as well. As I mentioned, these particular recorders are fantastic. I like the Eurotherm much better than I like the Honeywells. And I know there might be some people out there who state that the Honeywell makes a better recorder. However, I would disagree. Okay, and as I mentioned, make sure that you add the ground strap. So, plug the recorder in. Okay, we have power. It's passed the smoke test. Alright. Okay, now I will take 5 volts. Okay, now remember before what we had? At less than 3.5 volts. Now we have 5 volts in the 5 volt section. And wow, with that. Whew. This tells you now we have logic. So this will move in speed phase. Okay, now whilst we're at it, we're going to check what the 24 volts are. 24.47. Now I didn't write down the amounts before. I'm assuming it was like 23 volts. But what we're really interested in is what you're trying to see what the ripple is like. Okay, so we only have about 9 millivolts, 10 millivolts of ripple, so we're okay with that. Now if we had a current loop, we can actually check to see what kind of current ripple we have. That would be what we're really interested in, but it's acceptable for now. And lastly, let's see what we got for the 12 volts. 12.15 volts. Okay, and let's see what we have there for current. I mean for voltage, millivolts. Okay, we have 2.10. That's very good as far as AC ripple. Now let's check out what the 5 volts. What do we have for 5 volts ripple? Very low as well. So as you can see now, that cord is up and running. It says it's starting. This whole repair took me less than 15 minutes. It actually took me more time to write out the documentation and to explain it, but I hope this helped anybody out there. Please leave a comment below whether you like the video. If I get enough comments, I'll make other videos of other down and dirty repairs that are made on the quick and on the cheap. Thank you so much for watching.